I'm Phil Simpson from the EDA software planning team at Intel PSG based in San Jose. And today I'm going to present some material on partial reconfiguration of FPGAs. The material was jointly developed with Kaylin Brunham from our software engineering team in Toronto. So the talk is on the topic of verification of FPGA designs that use partial reconfiguration. So this presentation is mainly targeted towards hardware designers that are creating FPGA designs. It's also applicable to anybody that's creating a BSP for designs that use FPGAs. So there are ways to target FPGAs with software design flows such as PCle, and these rely on a BSP and take advantage of partial reconfiguration. The persons that are developing these BSPs can benefit from the techniques that we're going to present. Okay, so from an agenda perspective, it's pretty evenly split in that I'll spend probably about half the time just describing what partial reconfiguration is and some of the benefits of partial reconfiguration. And then the second half of the presentation will be very much focused on the verification challenges with PR and the techniques that we've put in place to help you conquer these challenges. And then we'll have the question and answers towards the end of the sessions. Now, while this presentation is in full screen mode, I don't actually see any of the sidebars on the app. So I will address all the questions at the end of the session. So starting with an FPGA. So FPGA, a field programmable gate array, it enables you to create logic. You can create custom logic and implement it in the device. So it gives you a lot of flexibility. So effectively, the design that you create is mapped directly onto the FPGA resources by synthesizing them into the physical implementation on the device. And what you really get is a configuration bit stream to program the device. The diagram that we show is a diagram from one of the Intel Arria 10 devices. Now, the reason I'm showing this is very important in that how the design is mapped to the logic will impact, one, the performance of the design that you implement, two, how long it takes to reconfigure the design, and three, it'll also impact how you can verify the design. So it's really the mapping of the design onto this floor plan is the key to success with partial reconfiguration. So if you look at the device floor plan, it's made up of core resources and periphery, where when we say periphery, it's anything that touches the pins on the devices, effectively goes out to the packages. So this is things like the I/O pins, the I/O PLLs, the HSSI blocks, which are high-speed interfaces, like PCI Express blocks, the hardened memory controllers. And then there's the core, which is effectively the ALMs, which is how the logic is implemented in the design, the block RAM, and the DSP blocks. So when you implement your design using partial reconfiguration, the design is going to be implemented into a mix of these resources. And how you select the area of the floor plan will determine how many resources are available and how the design needs to be implemented, which will impact the performance of the design. So, as mentioned, partial reconfiguration is a design flow where a section of the design that is implemented in the FPGA can be reprogrammed to a different functionality while the rest of the design continues to operate. So as such, as a designer, you need to create logical partitions in the design to identify the sections of the design that can be reconfigured versus the area of the designs that are not going to change. You do this at a logical level, but you also need to do it at a physical level. So this is where the floor plan becomes important. So you'll create a physical partition on the device floor plan to identify the resources available for the logical mapping. When you compile the design, you're going to get a configuration bit stream. This is what will program the device to implement the functionality. So you can get a bit stream for the whole device. So you program the whole device and it will operate. But you also get a partial bit stream for the parts of the design that's going to change. So this enables you to reprogram that area of the device with a smaller bit stream that implements the new functionality that you want to put into that part of the design. So as I mentioned, the device is usually initialized or configured with a bit stream that configures the static region. So when we say the static region, this is a part of the design that isn't going to change. So this will consist of everything that touches the pins, plus any other logic that you have in the design that does not need to change functionality. So once the design is functional, a partial bit stream is used to reconfigure the PR region to different functionality, while the rest of the design continues to operate. So in effect, the external interfaces of the device continue to operate while the reconfigurable portion of the design of the core is changed. So this diagram really shows you at a high level what can be changed. So anything related to the I/O, which we call the periphery, cannot be reconfigured with partial reconfiguration, but the core logic can. Now, the stuff that talks to the I/O, such as the transceivers and the PLLs, they can be reconfigured, but this is through a different operation. This is through dynamic reconfiguration, which is a separate process that can be performed in any FPGA design if planned for upfront. And this can be combined with partial reconfiguration as part of a flow. So really summarizing that, what this tells you is partial reconfiguration applies to memory, the DSP blocks, and to the logical blocks, or what we call the ALMs. Now what's key here is the logic blocks power up in a don't care condition, in an unknown condition. Typically in FPGA design, you have the option of specifying what condition your registers will power up to. And this is implemented by using a global reset after configuring the device. However, while this applies to the static region of the design, the area that's not going to change, for the area of the design that is partially reconfigurable, you cannot power up to a known condition. So you need to create the design such that you have a way of resetting these registers to a condition that will give you the functionality that you need. So let's look at some of the benefits of partial reconfiguration. First one, it allows external interfaces to remain active while you reconfigure a submodule. So effectively, your device can continue to take data through whatever interfaces, or it can continue to output data to memories or through other interfaces, while you reconfigure part of the design to effectively change functionality. So this is useful in that it helps eliminate in-field system downtime, in that if you want to update the functionality of something, you can do it without having to take the board down or without having to take the FPGA offline. Effectively, you can reduce the cost of the FPGA because you're really extending the FPGA, and that if you, based on a certain condition, you want to configure a block to have different functionality, rather than having all of those blocks already in a single FPGA, you can have some of that functionality stored externally, for example, in a flash or on a workstation, and then update them as needed. You can also put the device into low power mode, in that while a particular block of the FPGA is not being used, it gives you the option to put it into a low power mode. It's very useful in the case where if you've got multiple interfaces that you want to change on the fly, you can combine the dynamic reconfiguration capability of the transceivers together with the partial reconfiguration capability of the core logic to implement a different standard, for example, change into different variations on Ethernet. And it also gives you faster programming time in that doing a partial configuration gives you a shorter configuration time. Now, note programming time is directly proportional to the file size, and this is also impacted by how you floor plan the design. So looking at the key applications, we see this used a lot where FPGAs are attached over PCI Express. So effectively, ways where the FPGA acts as like accelerator over PCIe. You could have a host processor that's doing a lot of the processing, but for certain tasks that can be implemented faster in the FPGA, it'll communicate with the processor over PCI Express. So it's a way of accelerating certain tasks. Similar thing for HPS. Now, HPS is a hard processor subsystem. So in the case of Arria 10 and Stratix 10 devices, we have processor subsystems in the device. They're ARM-based. For Arria 10, it's A9. For Stratix 10, it's the A53 processor. And you can use the FPGA is often used where it acts as an accelerator to these processors. And similarly, you can communicate with the FPGA over Ethernet. As I mentioned, it gives you the ability to update the configuration without having to take the FPGA offline. And it really enables you to put parts of the FPGA in low power mode when you're not using them. And this is very useful for in the IoTG. This is very useful where you've got any handheld devices where you're running off a battery and you want to extend the life of that battery. So this particular diagram just shows one of the key applications. And the reason I show this one with the FPGA over PCIe, where the FPGA acts as an accelerator, towards the bottom of the screen you can see it shows OpenCL. So OpenCL is a software programming language. It's based on C, which enables you to write code where you identify what will run on the host processor and what will be accelerated on the FPGA. This software-based flow enables software engineers to target FPGAs without really having detailed knowledge of the FPGA itself. Now, from the perspective of verification, they'll be targeting a particular board with a particular board support package. The rest of this presentation in terms of the verification of partial reconfiguration applies to the engineers that create that board support package such that the software engineers can target the FPGA. So looking at the design steps for using partial reconfiguration, you'll create your initial working design, including the periphery and one of the implementations that you want to put in the partially reconfigurable region. Then you'll develop the additional logic for the different personas or the different functionality that you're going to put into the PR regions. You'll floor plan the design, where you'll identify the areas of the device that are going to be reconfigurable. And you'll have added in some specific PR logic. So we'll talk about that, and that's really where the crux of what we're going to focus on with verification is. There is specific logic that you have to put into a PR design that you don't have to put in a typical FPGA design. And this is used to perform the PR operation and also to take care of your PR region effectively going through a change of functionality where it will go from working as function A to being taken offline to working as function B. And we'll talk about that in a bit more detail. So there are some design challenges that are unique to partial reconfiguration. The first is that if you look at this diagram on the screen, you have to instantiate a PR IP core in your design. This controls the programming of the bit stream into the PR region, which is shown in the diagram. It ensures that the correct bit stream is applied to the PR region. Now, the design itself needs to be able to cope with the impact of the reconfiguration on the system. First part being part of the design going away and then coming back with different functionality. Now, during the reconfiguration operation, the outputs of the PR region will go into an undefined state. So your system design needs to be able to cope with these undefined states. So effectively, it needs to be able to prevent these undefined conditions propagating throughout the rest of the design and potentially corrupting your system's operation. So the diagram on the right here kind of shows a mux connected to the PR region with some additional signals. This is a sort of standard technique that is used, a standard method to mitigate the effect of these unknown conditions, where effectively when you're performing a PR operation by using this mux, you can force the outputs of the PR region, which are going to communicate with the rest of the design that typically doesn't change, into a known condition. Finally, the registers within the PR region itself will power up in an undefined condition. So traditionally in FPGA design, as I mentioned, registers can be powered up to a known condition. And this condition can be defined with initial conditions on the registers in the RTL. At power up, the global reset on the FPGA will initialize all the registers to the values that you've specified. However, in the case of partial reconfiguration, the registers in the static region, the part of the design that isn't going to change, cannot be reset. You want that to continue to operate, which means you cannot perform a global reset. What this means is you cannot bring the registers in the PR region, you cannot power them up to a known value. Now, if you performed an RTL simulation on that PR region where you've used initial conditions in your code, the simulation will show the design to operate as correctly, as the registers will assume the initial conditions of the power-up state. However, when you implement it on silicon, they're going to come up in an unknown condition. And this could cause your system to stop, not to function the way you expect it to function. Now, the traditional approach to debug these types of problems has been test the design on the silicon, run it on the silicon. However, while you can be successful with this, it can be very difficult to isolate the cause of a problem. This particular picture shows the freeze bridge or the mux that you'll use in your design to isolate the PR region from the static region, such that you can put the outputs into a known condition, the input into the static region into a known condition. Now, the unique thing here is the operation of how this works. They'll only really test this during a PR operation, because that is at the point that you're actually going to activate the mux to force it to a known condition. So as mentioned, if this logic isn't working adequately, your system can freeze or you'll lock up the hardware. Then the second problem is within the PR region itself. The PR region will come up with the registers in an unknown condition. So what you need to ensure is that you've got the right reset sequence in place to bring the PR region into a known good state before you release the freeze bridge to allow the signals to drive correctly into the static region. And this presentation is going to address problems 1 and 2. It's going to show how you can achieve this through simulation. So if I look at a simple example that demonstrates the problem, I got a little design of a counter here that we call unsafe counter. And in it, you can see that we use initialization conditions to bring the counter up at logic value 0. Now, this is interpreted as power up conditions on the registers. If you perform an RTL simulation, everything will look great. The device will work as you expect. However, if you look at the waveform, and particularly at the area where I've highlighted the PR, if you look at the post-synthesis, so the the design after it's been mapped to the FPGA resources, what you see is the registers are in an unknown condition. And in the case of the unsafe counter, it never comes out of that unsafe condition. There is no reset operation as part of this code. Therefore, the counter never operates as expected. I've also shown a safe counter, so this would be a version of the design where we do have a reset sequence in place. So again, you see it comes up in an unknown condition. Then a reset operation is performed with the PR logic reset end signal. It's shown between M2 and M3 on the diagram. And this resets the counter to 0, and then it begins the count as you'd expect. So this kind of highlights the kind of problem you've got. What makes this tricky to debug on silicon, if you had the unsafe counter, is that you don't know what condition it's going to come up in. So sometimes when you power up, it just might power up at logic value 0, and it will continue to count as you expect. And you'll think your device is working fine, but then the next time you load that particular image, it will power up in some other unknown condition and start to fail randomly. This is why this can be quite hard to debug in silicon, but it's something that can be completely prevented through the verification methodology that we're going to describe. So the solution that we've provided is a system Verilog test bench methodology for partial reconfiguration. It enables you to test the design going into and coming out of a PR operation, allows you to verify that your user freeze bridge is operating as you'd expect it to operate, and that your partial reconfiguration logic resets to a known good condition. The environment that we provide can also be integrated into a UVM environment. So how do we do this? We model the physical effect of the registers powering up in an unknown condition. And we do this by being able to use a post-synthesis map netlist, so that at this point, your design has been mapped to use the resources within the FPGA design. So using this technology map netlist, we then are looking at the behavior of the design on silicon as opposed to the behavioral model. We use this for the PR region of the design. We continue to use the behavioral model for the rest of the design. It's not going to change. It doesn't suffer from the don't care conditions. It'll power up to a known good condition. The models allow you to asynchronously load 0, 1, don't cares, rands into the registers, depending on how aggressive you want to be on your verification. And the models are lookup tables. So the lookup tables is the logic in an FPGA that implements the combinational logic, are all X pessimistic, so they will transfer the X, the don't care conditions. So this is a block diagram of the environment that we've put in place. We provide simulation models for the PR control block. We provide wrapper files, which are shown here around the yellow region that I'll talk about in a little bit more detail, which is used to simulate the loading of a new persona into the design, so effectively the switching of the personas. And we also provide several test bench components that can be used in a UVM environment. Now, that's part of the solution. The other part of the solution is the software design tools, so the Quartus software. The Quartus Prime Pro software also generates the technology map simulation netlist for each of the personas that are in the design. So each of the personas that will target the PR region. And we'll talk about these in a little bit more detail on the next slides. Okay. So in order to enable the simulation of the reconfiguration of multi-personas, each of the personas simulation models are instantiated in a wrapper file. Now this wrapper file has muxes on the inputs and the outputs. The mux the input into and out of the personas to the rest of the design. The PR select line controls which particular persona is going to be selected and is going to be operational. And it has been implemented as part of a system Verilog interface. The PR select can be driven either by the PR control block simulation model or directly from the simulation test bench. Driving it from the control block is useful for doing a full simulation of a PR operation. So based on the top level design, doing a full configuration. The simulation test bench approach is useful if you want to do a simulation at a block level. The sequence for switching personas is you would first assert PR activate, saying I'm going to do a partial reconfiguration. Then use the PR select to switch the PR persona. Then deassert the PR activate. This way you've now switched the persona. You've emulated the switching of the personas. And the PR persona that is about to be tested is always set to having all the registers storing X or don't care condition or any other initialization value that you want to write to it. Now the output mux itself can drive don't care conditions while PR activate is inserted. So this enables you to emulate the outputs of the PR region being undefined during a PR operation. And this is a fast way of enabling you to test that your freeze bridge is operating the way you expect. The EDA netlister in the Quartus Prime Pro software creates the tech map simulation netlist for each of the personas, as well as creating a script that will then create the wrapper file, which is based upon the number of potential personas in your design and the module definition that you actually have. You can use the original RTL for the personas in place of the tech map netlist, which will give you faster simulation, and that enables the emulation of the switching of a persona and the driving of X's to the PR region outputs using the mux and the wrapper. So it's useful for testing when you do a PR operation. Can your freeze bridge cope with the don't care conditions? However, if you want to check that the personas themselves are operating as expected, you need to capture the physical behavior of the inferred registers. And to do that, you need to use that post-synthesis tech map simulation netlist. This captures the potential problems with the registers powering up to an unknown state. Now, the PR control block, it accepts the partial reconfiguration bit stream and reconfigures the appropriate portion of the device. So it'll reconfigure the PR region in the device. It has a number of control signals such as ready to accept the PR bit stream, PR success, PR error, etc. Delivering a PR bit stream, so it's the programming file, to the PR control block will produce the expected stimulus of the PR control block signals and allows the switching of the PR persona in the PR region. The model uses a simulation partial bit stream from which it interprets the instructions to drive the two simulation ports that are SimState and SimPRID. These are actually connected to a system Verilog interface that allows monitoring of the state of the control block. These in turn can be connected to higher level components such as the monitor and driver that are shown here in red at the top of the diagram. The monitor does, as it's described, it monitors the simulation ports in the control block. And when a PR activate event is detected, it generates a transaction to the PR region driver to assert the PR select line, causing the PR region to switch the active persona to the persona that you've specified. It also takes care of the coordinating with driving the PR activate line, turning it on before doing the PR select, and then turning it off again. So in short, this describes describes the PR simulation environment that we are providing. So in summary, it's the logical to physical mapping in a PR design that creates some of the unique verification challenges that can only be uncovered during the partial reconfiguration operation on an FPGA device. Traditionally, it has only been possible to debug problems that occur as a result of partial reconfiguration operation on a board. However, this type of solution to verifying it makes it hard to isolate the source of the problem. The methodology that we've described in this presentation, it enables designers to simulate the partial reconfiguration operation on a design and to verify that the static and reconfigurable portion of the design function as expected. You can detect problems before you go to the board, so that when you're at the board, you're now looking at things from a system level, making sure that your whole system works the way you expected, as opposed to having to try and debug the configuration operation. This methodology that we've described, it combines a mixture of tech map netlists, so mapping to the physical implementation on the FPGA, together with behavioral simulation in a system Verilog simulation environment that is UVM compatible. So we've covered quite a bit of detail in quite a short time. What I've got on the screen now is some additional resources where you can get much more information. So we've got a lot of information available on GitHub. If you go to the links that are shown in the presentation here, we've got some reference designs that you can run on some of our development kits for Arria 10 and for Stratix 10. We got some tutorials that walk you through the flow of how to set up a project for partial reconfiguration, how to compile it, and then how to program the device successfully, again targeted at Arria 10 and Stratix 10 development kits. The Quartus Prime Pro handbook volume 1 of the handbook has got significant material on the partial reconfiguration flow, and just generally the FPGA partial reconfig site on GitHub contains information including more details on verification as described here under the verification folders. So with that, I've finished the presentations a little earlier than I expected, but I'll now turn it over to any questions. So I just received a question, is there an IoT simulator? What we actually provide is something to enable you to simulate the design that has been created in the FPGA for the IoT. There isn't a specific simulator, so the methodology that we've got, the verification environment that we provide, will work with all of the standard EDA simulators, so it'll work that support System Verilog. It'll work with the main 3 vendors from Synopsys, Mentor Graphics, and Cadence. Okay, and follow on to that question is there any, for the IoT simulator, is there anything for real-time projects? So I think this is more focused towards people that are creating embedded designs, so it's more typically what's running that's running on the processor. So we tend to have bus functional models for our processors that are included as part of the FPGA, and those bus functional models can be combined with what we've got that we described in this project, such that you can simulate your design again in any of the standard simulators. Now the simulator enables you to verify that your design is working. It does not actually create the design. That's another one of the questions that's come in. So if you want to create the design, You're going to do that if you're designing at the RTL level, you're going to do that in the Quartus project. That is where, if you're designing the BSP, you will be putting together the RTL portion of the BSP with all the interfaces inside of the Quartus Prime Pro tool. And then the design that you've put together and implemented there, it can be simulated in any third-party EDA simulator. If you're designing a project using OpenCL, you can, if you're designing the design in OpenCL, it's got its own verification environment that is included as part of the OpenCL toolchain. Okay, so I think the underlying question that I'm seeing is really somebody is putting together designs that target specific industries with regard to IoT, and they're looking for help as to how they can actually simulate the whole system. What we described here is really targeting what would be part of the system, so how you could ensure part of your system is working the way you expect. I think when you start getting into the realm of mixing hardware and software together and how you're going to perform that level of simulation, then you're going to be looking at a different class of simulator, and that's more something that would like to be handled with some of the modeling tools, such as either using System C modeling, or maybe moving into some of the tools that are available from other third-party companies, such as MathWorks and the like. But I don't think there is a specific IoT simulation tool available. It's a case of taking existing tools and performing a system simulation with what is the best environment for those tools. Any more questions? I think you can still submit them through the web app, and I'll get back to you. I'll happy to respond to the questions. Happy to give you more information in any way to help you with your partial reconfiguration designs or with the verification of your partial reconfiguration designs. Thank you very much.